Hey everybody, welcome to our study of Newton's law of universal gravitation. It's section 5.5 in our textbook, but here we go. So as we study these things, we look at Newton and how he discovered or how he thought about gravity, and while he didn't necessarily discover gravity, he was one of the first to explain how these things work, or the gravitational force is one of these field forces, this force or action at a distance is how he called it. And he noticed that the Fg, so we'll call this Fg, the force of gravity, is proportional to the two masses between the two objects. And so the force of gravity is proportional to m1 and m2. It's proportional to those two masses. And something important to note here, that this inversely proportional to the square of the distance basically varies as 1 over r squared, where the radius between the two things is the distance between the centers of mass. So if we look at two objects, we're looking at the center of the objects there. When we're talking about like a satellite orbiting Earth, we're talking about the center of the Earth to the center of mass of the other object. And so what we'll notice is this distance between the radius and that distance to the object. Sometimes we'll say the distance above the Earth, something like that. That's how we're going to express that. The other thing is this gravitational constant is called big G. And where we see that is the force of gravity, the way Newton describes it, is big G m1 m2 over r squared, where big G, the gravitational constant, is 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. And what we notice is this G value, this universal constant, is actually a very small number. So you can calculate the force of gravity between any two objects in the universe. So here what we'll do is we'll use two 75 kilogram people that are about a meter apart, 0.95. And so we have our basic calculation, Fg equals big G m1 m2 over r squared. So we'll plug all that in. We get about 4.2 times 10 to the negative 7th newtons worth of force between these two objects. So notice 10 to the negative 7th, this is an extremely small force. So we'll notice that gravity, we've always kind of said this, gravity is one of the weaker forces that we know about. And so we obviously can't feel the gravitational field or the gravitational pull between two objects as we sit on Earth. A pretty common question we'll see is something like this. A satellite weighs a certain amount of newtons on Earth, so that's the Fg of the object. And so we're going to figure out how much it would weigh if its mass is tripled and its orbital radius is doubled. And so what we do is, I like to draw a little sketch here. So we have this object sitting on the Earth, and then what we do is we're going to triple it, triple the mass, so 3m to m, and we're going to double the radius. That's kind of the idea what we have. So what we do is we envision that the first force of gravity, Fg1, is big G m1 m2 over r squared, and we know that it was 9,000 newtons. What the other thing told us is that we have this G m1 m2 over this double r. We're doubling the radius there, so we have to square that. And remember, we're tripling one of the radii there. And so what essentially happens is we have this 3 and 4, big G m1 m2 over r squared. So we see that 3/4 there. And so all we do is we get that 3/4, multiply it by the 9,000 to get what the object would weigh if we double and triple those things. So all we're really doing is figuring out what the ratio is right here based on that 3 and that 2 there. And so we just have to make sure that we understand that when the radius is doubled, tripled, whatever, we square that to make sure we understand what this 9,000 Newton object would weigh based on the orbital radius and the mass being tripled. Remember, the orbital radius, I'm going to go up to this thing again here, is the distance between the two centers of mass. And that's what we mean by the orbital radius. We've talked about this at little length before, but once again, it's worth mentioning. A satellite in orbit, what's happening is it's constantly falling around the Earth. It never falls straight down. It's always traveling to the left or right as much distance as it falls down. That's why it constantly feels weightless. That's kind of what we feel when we're in the elevator as it comes down under our feet. And so what we do is we figure out how, at what height or what the orbital radius is, what speed does it travel. And so one of the things that we have to remember is the object moving in a circle, yes or no? If it is, it does have some type of net force. So the centripetal force is the gravitational force. Gravity is the string that holds everything together. So if I look at it like this, I know that it's MAC equals this new gravitational law thing here. So if I finish filling out what the centripetal force is, I have this mv squared over r equals big G m1 m2 over r squared. So one of the things that we have to do is we have to kind of know what we're talking about here. We're going to consider the moon here in a little while. This is the mass of the Earth. I'm going to call this m sub e. And then the object orbiting, I'm just going to call it m sub 2. That's the satellite. And so we know what the radius is. That's the orbital radius there. And so what we do is the centripetal force, this guy right here, well, we have to use the mass of the satellite. We'll just call that m2. M1 is the thing providing the gravitational force or the gravitational field there. So notice what happens here is the masses or the M1s cancel, or the M2s cancel, sorry. The M2s cancel, leaving me with the M1 thing. So we have to figure out what the mass of the Earth is. That's a constant that you'll be given. The R's cancel, well, at least one of them does there, leaving me with what we call the satellite equation, if you will. V squared equals big G M1, or mass of the Earth, over R. And since we're looking for the speed, we say V equals G M sub E over R, mass of the Earth. So when I fill it in, it looks kind of like this. That's plugged everything in. So we end up getting a velocity of about 2,200 meters per second, which is about 49.21 miles per hour. So very fast. One thing to note, these things travel fast enough. So any type of GPS satellite, any satellite that we have orbiting the Earth needs relativistic calculations involved in order for the signal to make sense to here on Earth, because they move so fast, which is pretty fascinating when you think about it. So that's how you figure out how fast these things are moving around the Earth. Here we call this the quote-unquote satellite equation, but it came from knowing the centripetal force is caused by the force of gravity. And so a lot of our questions will involve figuring out which one of these things is known. And so not everything will always cancel that way, but the majority of the time, that's how those things work. Of particular importance here is the inverse square law. So I just wanted to kind of understand how that works. Hopefully remember from math that when we have the inverse square law, it looks something like this. As the numbers get very, very small, that number increases big time. As this number increases, this y value decreases big time. And so we remembered the Newton's gravitation looks like this. Fg equals big G m1, m2 over r squared. Well, and then we said that the force of gravity varies as the square of the distances between them. So what happens is if I have my FG up here on the y-axis, have my r over here on the x-axis, we notice that as this r value increases, the force of gravity is really, really small. As the radius decreases, as I start dividing by these increasingly smaller numbers, we see that the force of gravity increases exponentially. And so in class, we'll kind of look at how the black hole thing is significant when it comes into this. Just know that this force, as I get super small, increases exponentially. That's kind of responsible for how the whole black hole thing works. So once again, when we get into class, we'll examine that a little bit more closely. The last thing I want to look at here is how to calculate, or what is a geosynchronous satellite, how does that behave? And so obviously a geosynchronous satellite simply means that it stays above the Earth at some point. And so we have a couple of parameters here. One, determine the height above the Earth's surface that it has to be. How fast is it moving, and compare it to something orbiting 200 kilometers above the Earth's surface. So a couple of givens. We have the radius of the Earth at 6.38 times 10 to the 6th meters, and the mass of the Earth 5.98 times 10 to the 24th kilograms. Once again, constants, you'll be given those. And what we got to figure out is how high above the Earth's surface is that. So we understand that the force of gravity is the source of the centripetal force. That's what's holding everything together. So plugging things in, big G, gravitational constant, mass of the Earth, mass of the satellite over r squared is equal to the mass of the satellite, v squared over r. And so notice here we have two unknowns, v and r. And so we have to be able to resolve that somehow. I'm going to scoot this up a little bit here. And one of the things that we can draw upon is the fact that we know that the velocity is 2 pi r over big T. And that's important because, one, I know that it has to travel once around the planet. That T, the period, is 24 hours, which just so happens to be 86,400 seconds. So we can substitute those values into this equation up above to make it look something like this. Big G, mass of the Earth, over r equals the velocity. So notice the masses of the satellite ends up canceling to get something that looks like this. So v squared, I'm getting that v using that value for the right there, 2 pi r squared over t squared. Make this look a little more manageable. Big G, mass of the Earth, over r equals 4 pi squared r squared t squared. And then we have some kind of algebra that happens here. We get r cubed is equal to big G, gravitational constant, mass of the Earth, t squared over 4 pi squared. Notice, I now know everything I need to figure this out. I have t, the period of motion. I know pi, and I know the mass of the Earth, and obviously I know g, the gravitational constant. So we're going to end up taking the cube root of all this, so make sure we understand how to do that. When we plug everything in, we should get something like this, 4.22 times 10 to the 7th meters. But this is from the center of the Earth, or the planet. So what I have to understand is that the question is asking me for this chunk right here. So I simply subtract the radius of the Earth and get this value here, that 3.58 times 10 to the 7th meters above the Earth. So make sure when you're doing these kinds of questions, make sure we understand where my variables are sitting and what it's actually asking, because what you find may or may not be the solution to the answer there. So the next part of this is figuring out the speed of the satellite. So the first thing I want to look at is v equals 2 pi r over big T. Once again, I know T, the period of rotation, that 24 hours or 86,400 seconds. And I know r, remember r is what I found over here. That's the orbital radius of the planet, or of the object away from the center of the Earth. So I can use those values to get 2 pi, this 4.22 times 10 to the 7th meters. The T is 86,400. When I plug that in, I get about 3068 or 3068 meters per second. So once again, fast movers. These things are moving really very quickly around the planet. The last thing we want to look at is compare that to the speed of a satellite orbiting 200 kilometers above the Earth's surface. Once again, assuming the synchronous orbit there, the new radius has to be a little different. The radius here would be 6.38 times 10 to the 6th. That's the radius of the Earth, plus my 200 kilometers. So I kind of do it this way. I kind of cheat when I do this. There's my 200 kilometers, 200 times 10 to the 3rd. So I get this number that I'm going to use for my orbital radius, 6.58 times 10 to the 6th. And what I'm going to do, there's a couple of different ways to do this. There's a ratio that you could use, but I'm going to go back and use our quote-unquote our satellite equation that we got from understanding FC equals FG over here. So what I'll do is I'm going to start here. Big G, mass of the Earth over R equals V squared. And then take the square root of each side, so V is equal to the square root G, mass of the Earth, over the orbital radius. When I plug stuff in, 6.7, negative 11th, 5.58 times 10 to the 24th kilograms, mass of the Earth. The orbital radius that I used from above. So I get a speed of about 7520 meters per second. So looking at this speed here, that second speed, versus the 3068, because it's lower, it's got to go a lot faster in order to keep from being pulled down into the planet, which is kind of what we'd expect there. So it's kind of the same idea as the string in our lab got smaller, the speed had to also increase. So a lot of similarities we can draw there. All right, so one last thing that I want to look at. I'm looking at the ratio of orbital speeds. So these are questions that we see a lot when we start studying these kinds of things. What we'll do is we kind of look at the first object here, and we take, let's just assume that we're going to go out a distance of 3r, and this is its path here. We get this second object, we're going to put it 7r out, and we're going to call this a mass of 7m, and that guy down here, we're going to call him a mass of 4m. And so once again, we're looking here for a ratio of orbital speed. So this question is really similar to the last one we did, although we don't necessarily have to do as much because we really are just concerned about the ratio of speeds here for a particular reason. So when we look at this, we know that this is kind of our magic sauce right here. We have the Fg is equal to Fc. In other words, the centripetal force is provided by the gravitational force. We know that we have mv squared over r, and over here we have big G m1, m2 over r squared. What's happening here is, if we look at this guy right here, we can just call that m. When we look at the equation, when we analyze this, the m is the thing providing the gravitational force, while the object being orbited, that's what's going to go into the mv squared side. So when we look at this, when our equation kind of boils down, we get v squared equals, I'm going to say m sub e, like mass of the earth, or whatever the thing providing the force of gravity is. M sub e times big G over r. What we notice is that these radii are the things that's going to be, everything's going to be based on. So when I take a look at the orbital speed, this turns into V equals the mass of the Earth or thing providing gravitational force times big G over R. So we already figured out how to do that from that question before. That's this quote unquote satellite equation, although deriving it is important. So when I look at this, I know that the velocity of A looks something like this. Mass of the Earth thing times big G over 3R. The velocity of B looks something like this. Mass of the Earth, big G over 7R. A couple of really important things to note here. One, the mass of the individual objects doesn't seem to matter. When we did our satellite equation, those masses dropped out, leaving us only with the thing providing the gravitational force. The other big thing is it looks like it just depends completely on the distances. So that's really interesting. The way we want to end up solving this is, let's say we want to do the ratio of velocity of B to the velocity of A. When we look at this, we have MEG over 7R square root over MEG over 3R. We end up getting a ratio of the square root of 7 to the square root of 3 when everything starts dropping out. So when you see questions like this ratio of orbital speeds, you can go through and you can start plugging in a couple of dummy numbers and all that stuff, but understanding how this equation leads us to this guy right here and using just a couple of ratios will really help us in simplifying how to do these kinds of questions. All right, great work. Make sure you bring these notes and we'll start discussing first thing when we get into class. All right, thanks guys. Talk to you later. Bye.